Thank you. Were they there? Okay.
It's the new there.
All right, guys. So we're ready to start. Thank you. Okay. So we are going to start with the cellular basis of disease. All right. And where we left off was the acid-base balance. Okay. And we talked last week about the fact that pH is one of the most tightly regulated parameters of extracellular fluid. So the body's pH is very, very tightly regulated. And that's because when pH is too high or too low, what happens? Proteins denature, enzyme systems stop working, and basically your entire body shuts down, okay? So acid-base balance and the maintenance of acid-base balance is very, very important in the body. And one of the ways that the body does try to maintain acid-base balance is by employing the use of buffer systems. We talked about how there are several buffer systems, but the most important buffer system is the bicarbonate carbonic acid system, okay? And how in this system we use a metabolic byproduct that's very easy to find in the body, CO2, and in the presence of water and carbonic anhydrase, okay, we can produce carbonic acid. And then carbonic acid, which is a weak acid, dissociates into bicarbonate and a free hydrogen ion. Okay? And so all buffer systems are basically weak acids and weak bases that can either donate or absorb a hydrogen ion to a solution. Okay? And by doing that can help prevent changes in the pH of that solution if an acid or a base is added to it. Okay? This buffer system, which is so important to the body, is also actively regulated by two organ systems, the respiratory system and the kidneys. Okay? The respiratory system is controlling how much CO2 is available to form carbonic acid. Okay? So the respiratory system is controlling how much CO2 is available to form carbonic acid. And the kidneys are regulating how much bicarbonate and free hydrogen ions there are. Okay? The effects of the respiratory system are very rapid. We can compensate for pH changes within minutes to hours through the respiratory system. But the kidneys take much longer to compensate. Okay? It's a much slower effect, so hours to days. So we talked about some causes of acidosis and alkalosis. We talked about how if the respiratory system is responsible for the acid-base imbalance, then we label that a respiratory acidosis or alkalosis. And if the respiratory system is not the cause, then if there's some other cause, we tend to label that a metabolic cause. Okay? And there are many, many different versions of a metabolic cause. Okay? And so the causes of respiratory acidosis and alkalosis is essentially any change that causes either hyperventilation or the blowing off of too much CO2, which would cause what? Acidosis or alkalosis? Alkalosis. Or hypoventilation or the accumulation of CO2, right, which would cause acidosis. The metabolic causes of acidosis and alkalosis are numerous. Okay, we talked a lot about, or we talked some about these possible causes. All right. Interestingly, renal failure or renal dysfunction can actually be a cause of both acidosis and alkalosis. Okay, so the renal system can really produce both. So, when we're evaluating an acid-base disturbance, okay, when we're evaluating an acid-base disturbance, we are given essentially the ABGs, or the arterial blood gases, right? We're given the blood chemistry. So we know the pH of blood, we know the partial pressure of CO2, or the PCO2, which is the CO2 concentration in the blood. Okay, we know the pH. We're given the pH. We're given the PCO2, which is the amount of CO2 in the blood, and we're also given the bicarbonate concentration. Okay, and based on those values, we can know whether the person is obviously in acidosis or alkalosis based on the pH. And then based on what the PCO2 and the bicarbonate looks like, we can also determine if they're in respiratory or metabolic acidosis or alkalosis. Okay? So we can determine whether they're acidotic or alkalotic, and we can determine the cause, whether it's respiratory or metabolic. Okay? We can also additionally determine whether there is any compensation going on. Okay? Whether the metabolic system or the respiratory system is compensating, okay, and whether that compensation has not kicked in at all, right, and it's uncompensated, or whether it's partially compensated or fully compensated. Okay? And we can determine all of these things by just seeing those values. So I put together a little exercise for us to go through. Since what I recommend is you look through this this slide once we've done a few practice questions, just to review what these changes would be. And so just so you know, this part of the slide, this part of the slide is what happens immediately when we see a pH change caused by one of these causes, metabolic or respiratory. Okay, immediately what's what it's going to look like, and then once there's been compensation, what's going to happen. Okay, and this C with an arrow up or down means we have a compensation moving the pH value up or moving it down. Okay, so with that in mind, let's look at, put it together before class today, and it's in your modules and your files on Canvas. I'll just make it bigger here. Everybody see that okay? No? Bigger? Bigger or smaller? Somebody tell me. Bigger. Okay. Okay. So when we're evaluating pH, so basically these are the values that we're looking at in terms of normal. Okay. We get a value for pH. Okay. Blood work comes back and we get a value for pH, and normal range is 7.35 to 7.45. We will also, with blood gas analysis, which is a type of blood test, we will get the PaO2, which is the oxygen content of the blood. Okay, we'll get the CO2 content of the blood. We'll get the bicarbonate content, and the SaO2, which is the oxygen saturation. That's the hemoglobin saturation. Okay? Now, for our purpose, when we're evaluating the acid-base balance, we don't need to look at the oxygen values. Okay? That's not going to be necessary for us to look at. And if you're doing some practice questions that you find elsewhere and it's there, you don't focus too much on it. Okay? The information that we need is the pH, the PCO2, and the bicarbonate. Okay? So what we're going to do is we're going to do a couple of practice questions here. And let's start with the second practice question here. Okay? So the data that we're given is the pH is 7.5. Is that abnormal? Yes. High or low? So the patient has alkalosis. Okay? Good. The PCO2, the carbon dioxide content, is 42. Is that high or low? Normal, right? It's within normal limits. And then 35 is the bicarbonate level. Is that, it's high, right? High. Okay, so this is the data that we get. So I've tried to break it down into some steps. All right? Step 1. Oh, I'm sorry. I'm doing this. I have to do this simultaneously in 2 places. So number 2 is 7.5, 42, and 35. Okay? So I tried to break this down into some steps. Step 1. We evaluate pH, PCO2, and HCO3 and see what values are within normal limits, that's W and L, within normal limits, and what's abnormal, ABN. Okay? And one of these 3 possibilities is going to be the case. Either the pH is within normal limits, and both PCO2 and HCO3 are abnormal. In that case, we're fully compensated. Okay? Those 2 values, PCO2 and HCO3, one is the cause and the other reflects the compensation. One reflects the cause of the pH imbalance, the other reflects the compensation. So if the pH is normal and both values are abnormal, then there is compensation and it must be fully compensated because it's normal. Make sense? Or the second thing is possible. If pH, PCO2, and HCO3 are all abnormal, then it's partially compensated. Okay? It means that there is compensation going on, but it's not enough to make the pH normal. And you're partially compensated. And the third possibility is always a possibility and is the preferred thing going on. If pH, PCO2, and HCO3 are all within normal limits, then there's no acid-base imbalance. Okay? And what I didn't put in there, which, like I said, I did this right before class, is if pH is abnormal and only one, either PCO3 or PCO2 or HCO3 is abnormal, right? So only one is abnormal, then what? There's no compensation. It's uncompensated. Does that make sense? Does that make sense? Good. All right. So let's look at what is going on in that number 2. So number 2, pH is 7.5. So first let's do that first thing and evaluate what's normal and what's abnormal. So 7.5, that's abnormal. 42, that's normal. 35, that's abnormal, right? So the pH is high, but only one of these two values is abnormal. So that means that what kind of pH imbalance is this? Uncompensated. Okay? Which is really convenient because then it allows us to see what the cause is. Okay? Between PCO3 and bicarbonate, one is going to be the cause of this pH imbalance. And HCO3 is high, which is a base, causing the pH to be high. Okay? If HCO3 is the cause, it's metabolic. Okay? If HCO3 is the cause, then it's metabolic. So this person has what comes first in terms of the words? Do they know? Uncompensated metabolic alkalosis. Make sense? Uncompensated metabolic alkalosis. Good. So we decided it was uncompensated. So the next thing that we can do, the next step, I kind of jumped ahead, but if the pH is abnormal, determine if it's acidotic or alkalotic, right? So, and we just determined that person was alkalotic. And then step 3 is determining whether it's respiratory or metabolic. And there's 2 ways to do that. If you like memorizing, I've come up with super lame mnemonics. All right? I've come up with really lame mnemonics to remember what's what. So Rebecca acts in every play, respiratory acidosis, elevated PCO2. Maddie's act didn't help. Metabolic acidosis, decreased HCO3. Did Peter meet Rebecca alone? Decreased PCO2 means respiratory alkalosis. Even he met Maddie alone. Elevated HCO3. I told you they were lame. Metabolic alkalosis. Okay? Those are mnemonics. The other method, okay, is and I cannot take claim for this name, but it is the who's your daddy method. Okay? And basically, who's your daddy means looking at the pH, looking at the data, and figuring out what is the cause and what is the compensation. Okay? So who's responsible for this pH change? And the way you do that is you match the pH imbalance with the change. So if your PCO2 is low, right? PCO2 produces acids. So if PCO2 is low, that is an alkalotic change. Okay? If you have a pH that's alkalotic and you have low PCO2, which is an alkalotic change, that's the cause. Okay? High PCO2 is an acidotic change. All right? So if you have an acidotic pH and a high PCO2, that's the cause. And then HCO3 is the base. A low HCO3 is an acidotic change. High HCO3 is an alkalotic change. Okay? So let's do another one of these examples. And We'll do a couple of examples. Let's start with number 1. So, number 1, let's scan the data and decide what is normal and what's not normal. So pH is 7.41, normal. PCO3 is 40, normal. HCO3 is 24, normal. This person is fine. Okay? So the answer is no pH imbalance. Number 3, super not normal, right? What do they have? Acidosis, that's right. PCO2 is 40. Is that within normal limits? Yes. HCO3 is 5. That's very low. Okay? Now, yeah.
So in this case, do you think there is a problem with CO2 in the respiratory system? What I think that it is a mixture of metabolic and respiratory outlets, because the system has to compensate the respiratory. And this case is not compensated.
See, you're too smart for this. That's the problem. No, you're right. You're right. So the reason, okay, so let's get through the question. I'm going to address what you're saying because you're absolutely right. But you're thinking about it at a much higher level, which is fantastic. Okay, so let's just look at it from on its face. Okay, the kind of acidosis the person has is from the face of it caused by this low HCO3, right? That is the cause. So a low HCO3 is an acidotic change. That makes sense? It's a base. If you don't have enough of it, right, it promotes acidosis. So the person's acidotic. It's clearly what kind of acidosis? Metabolic, okay? And is this partially compensated, fully compensated, uncompensated? Uncompensated. Because the PCO3 is within normal limits. Okay? So, based on the values, what we have here is an uncompensated metabolic alkalosis. Acidosis, thank you. All right, an uncompensated metabolic acidosis. So, to your question, how quickly does respiratory compensation kick in? Very, very quickly. Okay? So the fact that the respiratory system is not compensating, it is contributing to this pH imbalance. Okay? Because it is not usual to get to the point where you're taking labs on somebody and they have a metabolic problem and the respiratory system hasn't started compensating at all. Okay? Does everybody understand that point? And that's a very important point. To see that the metabolic system hasn't kicked in is not unusual, but to see that the respiratory system hasn't started compensating is unusual. Okay? Good. Let's look at the next one. 7.26, is that abnormal? Abnormal. And it's what? Acidotic, that's right. 63, is that within normal limits? No. That's high, correct? High PCO2 is what kind of change? An acidotic change, okay? And then HCO3 is 25, is that's normal, okay? So the fact that pH is abnormal and only one of these two is abnormal means it's what? Uncompensated. And then PCO2 is elevated, which is an acidotic change that matches the acidosis. So this is an uncompensated what? Respiratory acidosis. Make sense? Good. Number 5. 7.52, normal or not normal? Abnormal, and it is what? Too high. That's right, so it's alkalotic. PCO2 is 18. It's very low. What kind of change is that? It's an alkalotic change. 25, within normal limits. Okay, so pH is abnormal, and only one of these two is abnormal. This is what? Uncompensated respiratory alkalosis. Yes, please.
So this numbers are real numbers or just two numbers?
Are they real numbers or are they? They're. I did not make these particular numbers up. I made the numbers that are below this up. But I just got it from an NCLEX practice site.
Because physiologically it's not possible.
It's not possible for. You mean in terms of the magnitude of the pH change and the?
For example, if you have CO2 is 18,
Mm-hmm.
chemically the bicarbonate has to decrease. It cannot stay normal.
That's a good point. That's a good point.
I'm not talking about the compensation.
No. I know what you're talking about. Yeah. So. No, I love it. I love it. It's really good. So I'm going to mention this. I'm going to mention it what he's talking about. So first of all, let's just pretend these numbers are like play numbers for us to practice on. And this is what we're doing in terms of finding the answers. But what he's saying here is if the PCO2 is 18, then the HCO3 can't be 25. Because why? Somebody tell me. Where does HCO3 come from? CO2. Okay? It's coming from CO2. So the actual bicarbonate level of the body, it is going to be based on compensation and activity of the renal system, but it also is going to be based on PCO2 and how much CO2 is there to form bicarbonate. Okay, so what he's so very astutely pointing out is that these numbers are clearly made up because if your PCO2 is 18, you don't actually have enough CO2 to have the bicarbonate be that high. Right? So that's a very good point. So you can see that the HCO3 gets a little bit complex. What determines HCO3 gets a little complex. But the basics of trying to evaluate pH imbalances is what I'm describing. Okay? Is the process of evaluating pH, determining the values for PCO2 and HCO3, determining whether it's compensated or uncompensated or partially, and then matching the imbalance with the respiratory or metabolic. Yes?
If that were true then we would never have an imbalanced pH, right? So with that thought process, and you're saying, oh, my bicarb should be lower, like that's not necessarily true. That could be someone's actual ABE. But if somebody's, that he's saying that, oh, your bicarb would automatically correct, well then everything.
That's not what he's saying. That's not what he's saying.
He's saying we compensate, correct?
No, it's not what he's saying.
I thought you were saying that couldn't be a correct ABG because your bicarb should be lower. My misunderstanding what you said. Because my point of view, if that were to be happening, your pH would always be lower.
Okay, I think that So it isn't what he's saying. He's not saying that the bicarb should be lower because it would compensate, right? What he's saying is that the bicarb, so a PCO2 of 18 is really, really low, okay? And with a PCO2 of 18, you actually don't have enough CO2 to produce that much bicarbonate, okay? So realistically, the PCO2, if it really were 18, this would be lower just because you don't have enough CO2 to form the bicarb, which would actually mean that this would still be alkalotic, which is not as high. You get what I'm saying?
I get what you're saying.
Yeah. So the what determines HCO3 is two things. It is the buffer system and the action of the kidneys, but it's also how much CO2 is there to form bicarbonate. Yeah. Okay. So is everybody comfortable with these things that we're working on here, that we've been working on? So what I recommend is you go and as you're studying, you complete 6, 7, 8 yourself, okay? Using this method. Yes.
I looked over 6 just now.
Yes.
My question to you is, how do you determine when?
Oh yeah. 6 is fun. Okay. I'm sorry. Go ahead.
How do you determine whether or not it's respiratory or metabolic?
Okay. So with number 6, you've got. Let's look at here. So you got 7.49. Okay. You've got 7.49. The PCO2 is 48, and the HCO3 is 33. Okay. So 7.49 is alkalotic. So basically, are any of these numbers normal? No. Which means if they're all abnormal, we know that this is what? Partially compensated. Which means that one is the compensation and one is the cause. So we've got an alkalosis, pH is alkalotic. PCO2 is 48. Is that high or low? It's high. Now, it's high. Is that a acidotic change or an alkalotic change? Acidotic change. Does that match the pH? Which means that must be what? The compensation. Right? While HCO3 is 33. Is that high or low? Is HCO3 being high an acidotic change or an alkalotic change? Alkalotic. Does that match the pH imbalance? Yes. So that must be the cause.
So, is it a partially compensated respiratory alkalosis?
It is a partially compensated metabolic alkalosis. Because HCO3 is the cause, it's metabolic. Okay? Yes, sir. Please. Yeah.
Number 7.
Yes, sir. Oh, yeah.
Is it possible to say this case is respiratory acidosis and metabolic
Metabolic.
alkalosis?
So let's go through it. Let's go through 7, okay? Let's go through 7. 7, the pH. No. Yeah. Okay. pH is 7.35. Normal. Okay? It squeaks in at normal. PCO2 and HCO3, are they both normal, both abnormal? Both are abnormal. So we know that this is what? Partially compensated. Oh, excuse me. We know it's fully. So that's another thing. Thank you. We have a normal pH and abnormal PCO3 and HCO3, PCO2 and HCO3. Okay, which means that this is not a normal person with a normal acid-base balance because these values are abnormal. So we know that this is fully compensated. Okay? A fully compensated what? We don't know. We have to figure that out. So first of all, when you have full compensation, the pH will be closer to one end of that range versus another. Right? So 7.35 is closer to what end of the range? The acidotic range. Right? So we're likely looking at a fully compensated acidosis. So now we have to decide, since it's a fully compensated acidosis, we have to decide what change matches that acidosis. Okay? So we said PCO2 is high and HCO3 is high. Which of those two alterations, the high PCO2 or the high HCO3, is an acidotic change? CO2. Okay? So CO2 is 50, meaning that this is a fully compensated respiratory acidosis, and the high HCO3 is what compensated it. Does that make sense? That's what compensated it. Does that make sense to you?
Yeah, I know, but there is a possibility. It's not only kidney compensation, but also there is going to be a lot of disturbances that cause the bicarb.
Is causing the bicarb to what?
Maybe
The-
there is vomiting. Maybe the patient is vomiting in acids. That's why the bicarb is high. That's why I said I don't like the body compensated because the body never compensates to normal people.
You're right. You're right.
Yes, when you have a normal pH, that means you have a mixture of disturbances.
Yes. So whenever you have something that appears fully compensated, you're absolutely right. That, and I threw this in just so that we could identify, that variation. But you're absolutely right that when people have acid-base imbalances, they almost never fully compensate, right? But if you do see a full compensation, it's likely that it's a much more complicated picture. That's a very good point. That's a very good point. Yes, ma'am.
Just for the sake of studying it
Yes.
and being able to apply the concepts, is it just easier to think of the full compensation like it's swung one way drastically so that there's like a dysfunction of some sort, and so it's swinging back the other way in order to try and balance itself out?
Yeah, that's right. That's right.
Okay.
Yeah. I mean yes, ma'am.
How often do you get overcompensation with the bicarbonate? How often do you get overcompensation for that last problem, or number 7? You said if the pH was closer to acidic, but if it was alkalosis, does it ever just swing down too far because the body doesn't quite know how?
No, it's not likely. No, it's not likely. There is a limit to how much the body can compensate. Yeah. Yes, ma'am. That's right. Yes, ma'am.
Respiratory and metabolic, because I didn't.
Say that again.
Respiratory and metabolic, what's the, like, how do you,
How do you distinguish that? The way you distinguish between respiratory and metabolic is one of those two ways that I mentioned. Okay, you can either use the mnemonic, or you can identify which is the cause based on the direction of the change.
so whatever is the cause of the respiratory, I mean, if the CO2 is high, that's the respiratory.
If it's acidotic, yeah. So I recommend reviewing this, right, and just going through these problems again. All right. Yes, ma'am. Guys, I can't hear. I can't hear. Good question. So if bicarbonate is high, what is that going to? So a bicarb is what? An acid or a base? It's a base. So if bicarb is high, it's going to tend to make the pH what? Higher, alkalotic. Okay. So the respiratory system is trying to go in the opposite direction to try to compensate. So what the respiratory system is going to do is try to increase the CO2, right? And how do we increase CO2? Hypoventilating, right? By not breathing as much in order to accumulate CO2. That make sense? All right? Okay, I'm going to move on from this. I know it's complicated, and hopefully I didn't confuse you too much. You want to go over 8 for chucks and giggles? Okay. All right. Let's just round things out. Number 8. So pH is 7.28. It's low, right? The PCO2 is 30, which is low, and the HCO3 is 15, which is low. So they're all abnormal, which tells us it's what? Partially compensated. And since 7.28 is low, then we're dealing with what kind of problem? Acidosis. So now we got to decide who's your daddy, right? Which one is the cause, which is the compensation. So we have an acidotic change. PCO2 is low. That's an alkalotic change, right? PCO2 produces acid. If it's low, that's an alkalotic change. Does that match the pH? No. That you are not the daddy. That's right. It's all of a sudden Maury Povich in here. Yeah. So that is, if that's not the cause, it's the what? Compensation. So HCO3 is 15, and that is low. Is that an alkalotic change or an acidotic change? Acidotic change. That matches the pH imbalance, right? So that's the cause. So this is a partially compensated metabolic acidosis. That makes you bet. All right. Okay. So you can Google more examples if you want. You could go through this again, but give a whirl at my steps. Okay. They actually make more sense than I'm explaining right now if you're reading it. And hopefully you can work through that. All right? Okay, so back to cellular basis of disease. So we're still talking about these aspects of the body's function that needs to be maintained in order to maintain cell function. Okay, so another thing that needs to be maintained within normal limits is cell metabolism. So cell metabolism involves the utilization of energy substrate, right, which is a fancy term for food. Okay, energy substrate in the form of proteins, carbohydrates, and fats, and using that substrate to form energy in the form of ATP. Okay, to synthesize ATP. Now, cell metabolism has 3 basic steps. We've got glycolysis. Okay, so carbohydrates and sugars go through glycolysis, and then the next step, and glycolysis happens in the cytosol of the cell. Okay, so it doesn't happen within an organelle. Then the next step is the next two steps is happening within the mitochondria, and it involves the citric acid cycle, also known as the Krebs cycle, and oxidative phosphorylation. Okay? So if I look at it this way, for every molecule of glucose, glycolysis will yield 2 ATP. The citric acid cycle or the Krebs cycle will yield another 2 ATP. And then the electron transport chain and oxidative phosphorylation yields 32 ATP. Okay? These 3 steps in metabolism, this last step, right, the oxidative phosphorylation, is the only step that consumes oxygen. And it is actually the only purpose for oxygen in our body, is in order to form this whopping amount of ATP. Okay?
How much was it?
32. Okay. So the vast majority of the ATP produced by the cell requires the consumption of oxygen. So when we talk, we're going to talk later about hypoxic injury to the cells or oxygen deprivation to cells. The nature of the injury is this inability to metabolize ATP, which means that the cell can no longer do work. Okay? And one of the things that starts to stop functioning when your cells can't produce enough ATP is they can't work those sodium-potassium ATP pumps. Okay, those pumps that I talked about last week. And when that happens, sodium accumulates in the cell, which means water accumulates in the cell, and you get these swollen, bloated, dying cells. Okay, so we're going to look at that later, but cell metabolism, because of this final step in ATP formation, cell metabolism is highly dependent on oxygen. Okay. And then cells in our body, highly dependent on oxygen. Cells in our body require adequate what in order to be provided oxygen? Yeah, so the cells in our body, the cells in our heart, for example, requires adequate what in order to get that oxygen? Blood supply, right? Blood flow. So hypoxic injury oftentimes goes hand in hand with ischemic injury, which is a reduction in blood flow to the area. Okay, so we're going to hopefully put this all together as we go along. So controlling cell transport is another aspect that needs to be done in order to maintain cell health. And hopefully last week you reviewed all of these aspects of cell transport: passive transport, active transport. Okay? If not, then I recommend that you review them, or if you had issues with the quiz questions, I recommend that you review them. Okay? Okay. So this idea that there is a cellular basis of disease, or that at the basis of disease development is cell stress and cell injury. The cells in our body are constantly under different forms of stress, and this is actually a healthy thing. Stress is a healthy thing within reason, because stress triggers adaptations to stress. Okay? And so a normal amount of stress or a healthy amount of stress promotes a healthy adaptation and greater resilience. Okay? However, sometimes the stress is unhealthy in nature or disproportionate. Okay, and sometimes the stress can actually be can qualify it as just an injury. Okay, so but the reality is that the cells, whether it's healthy or unhealthy stress, still adapt in order to try to maintain integrity and maintain function. Okay, and the adaptations to stress and injury change the way the cell functions, which changes the way the tissue and organ functions, which begin to manifest as signs and symptoms of disease. Okay? So when we talk about stress, an example of stress is an increased functional demand. We'll see that a lot as we go through the semester, that in the development of disease, something happens which increases functional demand of the tissue. Okay? And if that increased functional demand is too high and too prolonged, it does represent injury. So these adaptations to stress and injury can take the form of things like hypertrophy, hyperplasia, atrophy, okay, and we're going to talk about what that looks like. It can cause a change in intracellular storage of material or the way that the cells organize in the tissue. Metaplasia and dysplasia are abnormalities in cell differentiation or tissue composition. Okay? Now, for this kind of level stress and these types of adaptations, if the stressor is taken away, the tissue rebounds and normalizes. Okay? So these types of adaptations generally are reversible. And mild forms of injury are also often cause reversible cell injury. But if it's severe enough and causes irreversible cell injury, that causes cell death. And there's a very generic term for tissue death, and that's coagulative necrosis. Okay. So necrosis refers to cell death as a result of external injury. Okay. And we're going to talk about another type of cell death called apoptosis, which is actually cell suicide. Okay? It's programmed cell death. And it looks very, very different from necrosis.
Like
Histologically, it looks very different from necrosis, exactly. Okay. Ugh. All right. Nick, can I ask you to help me with this, actually? Do you mind being here and then when I change the slide, you change the slide? Thank you. I'm sorry. Okay, we can go to the next one. Yeah. Nick has a very skilled, very high skill set. All right. Okay. So I know that you guys are probably ready for a break. But let me just say this. So if you go up one more time, just to recap, this is what I was saying about stress, adaptation to stress, okay, and these different morphological changes that occur as a result of persistent stress or mild injury, and then severe injury results in irreversible injury and necrosis, essentially. Okay? All right. So there are many, many forms of cell injury, okay? Many mechanisms of cell injury. We're really focusing on just a few examples, okay? And two in particular because they are so common. One is hypoxic injury. This is injury caused by decreased oxygen supply to the tissue, okay? Often caused by ischemia. Okay, ischemia refers to low blood supply or blood flow to the area. And since the blood is carrying the oxygen, it results in hypoxia. Anoxia is a term that describes the complete cessation of oxygen delivery. So when, for example, we've got a complete obstruction of blood flow to an area, it will create an anoxic injury.
So it's not necessarily like when you're lack of oxygen. So like if you're not breathing, then it can be anoxic too, right? Because you're not getting.
Let's talk about that later. Yeah, it's a little complicated. So, if hypoxic injury, is bad in and of itself, but we even see injury with reperfusion of an area. So when you have ischemia or an obstruction of blood flow to an area that triggers hypoxia, when we reperfuse the area, we often cause something called reperfusion injury. And the nature of reperfusion injury is, and stay with me for a second here, when we cause hypoxic injury, we cause an inflammatory response. Okay? Any kind of tissue injury causes inflammation. Now, when we return blood flow, what we're also returning are, we're promoting the entry of white blood cells to the area that are going to release reactive oxygen species and potentially cause more injury. Okay, so reperfusion injury is really inflammatory injury that's made worse when blood flow returns. And then we're also going to talk about injury in the form of free radicals or reactive oxygen species. Okay? And a free radical is any element with an unpaired electron in its outermost shell. Okay? So any atom with an unpaired electron in its outermost shell. Because electrons do not like to be by themselves. They're very needy. Okay? So an unpaired electron will steal an electron from any bond that it comes in contact with and will therefore cause damage. And now while we are used to seeing oxygen in the form of O2, right, which is not a free radical, there are other forms of oxygen that are free radicals, and we call those reactive oxygen species. Okay. And when they are present, they cause damage like what we call lipid peroxidation or damage to lipids, the same kind of lipids we see in the plasma membrane, disruption of polypeptide chains, so damage to proteins, and DNA damage. Okay. So we're going to look at that a little bit more closely. Let's take a 10-minute break now and come back and continue.
Thank you.